Okay, so this is EDCO A and it's question 11, and we're looking at indices. Specifically in the first part we're going to take a look at scientific notation, and we'll do a few examples of that before we answer the actual question given. And then the second part, the B part of the question, is more interested in indices and the rules of indices specifically, which I have typed out and I have here on the right hand side. So scientific notation is a way for us to write really large numbers in a more manageable way, and we can also write really small numbers in a more manageable way as well. So let's have a look. First of all, if I have a large number, for example, we'll go with 43 million, and I'm interested in writing this in scientific notation. So over on the left hand side here we can see the form that scientific notation takes. We're looking for some number between 1 and 10, that's A, times 10 to a certain power, which we're going to call n. And so what we need to do to fill in scientific notation is we need to figure out what the A is going to be and what the n is going to be. So A is going to be a number between 1 and 10. We take the first digit of our number, which is 4, and we write that down. And if there's digits after that, we put them after a decimal point. So we say 4.3 in this case. If there was another number after the 3 other than a 0, we put down that number as well. So 4.3 is the A, the number between 1 and 10. And then we are going to say times 10 to the power of n, where n is the number of digits after the first digit. So if we count them, we have 1, 2, 3, 4, 5, 6, 7. So there's 7 digits after the first digit, and that's scientific notation. Sometimes they'll ask you to write scientific notation to a certain amount of decimals or a certain amount of significant figures. In this example here, we've just written it exactly as the answer should be. So let's have another example. Let's have 731,432,000. So this is our number, and again we want to write this in scientific notation. We start by picking a number between 1 and 10. So we write down the first digit, which is 7. Put our decimal point, and in this question we're going to write the answer to 2 decimal places, and so I'm just going to write down the 3 and the 1. Now note, we would have had to look at the number after the 1, which is a 4, to make sure that it wasn't 5 or bigger. If it was 5 or bigger, we'd have to round up to 7.32. So 7.31 is our number between 1 and 10, and then multiplied by 10 to the power of the number of digits after the first digit. So we have a 7, and then we have 1, 2, 3, 4, 5, 6, 7, 8. And so in this example, our scientific notation is 7.31 times 10 to the power of 8. This answer isn't as accurate as our first answer, because in the second answer we've rounded off to 2 decimal places, but still a reasonable way to write a very large number so that it can be used then for other things in a more manageable way. Okay, just to briefly look at small numbers, even though the example we're going to use is obviously a really big number, we just want to have a quick look at how we would write really small numbers as well, because that's something we can be asked to do with scientific notation. So we'll just erase this, and what we're going to do is we're just going to write down a really small number. So for example, 0.0000421. So in this example, what we do is we again want to write down a number between 1 and 10. That's going to be the A. But obviously we're not going to start with the first digit, which is 0. And we have zeros all along until we get to the 4. And so the 4 is the number I'm going to write down. And then 0.21. So you write down the first non-zero digit, and then we have our decimal point, and then the numbers after it. Now this time, to figure out what our power is going to be, we count the number of zeros. So we have 1, 2, 3, 4, 5, and because it's a really small number, we put in a minus. So 4.21 times 10 to the minus 5. So when we're doing really big numbers, we don't count the number of zeros, we count the number of digits after the first digit. When we're doing really small numbers, we count the number of leading zeros. Okay, so let's have a look at another example. So let's say we have 0.000000527, and I want to write this answer to, let's say 1 decimal place. So again, I pick a number between 1 and 10. So I go until I get my first non-zero, which is 5, and then point. Now because I want one decimal place, I take a look at the next number, which is a 2, and the number after that is 5 or bigger. And so I'm going to have to round up. So here's my 2, that's the next decimal. But the next number is a 7, which is bigger than 5. And so we have 5.3 times 10 to the power of. Now how many zeros have we? 1, 2, 3, 4, 5, 6, 7 zeros. And we include the 0 to the left of the decimal and then any zeros that come after it. So let's go and have a look at our example. So we're told that our nearest star is Alpha Centauri. So we have an image of it here on the right hand side. And the distance from our sun, Alpha Centauri, is given by this massive number here. But this number is given in meters. And then we're asked to write this in scientific notation, but in kilometers. So the first thing I'm going to do is I'm going to convert that number into kilometers. So 1 kilometer is equal to 1,000 meters, and so if I divide this large number by 1,000, I'll have converted it into kilometers. So I'm going to chop off the last 3 zeros because that's equivalent to dividing by 1,000. So I'm going to write down the number again: 41600 000 000 000 000. So this is our large number. It's a bit smaller because it's now in kilometers. And what we're going to do is convert this into scientific notation. So I'm going to write it in the form a times 10 to the power of n. So a is a number between 1 and 10. So we're going to write down the first digit 4 and then 0.16. We're not asked to give our answer to a particular amount of decimal places or significant figures. So we're going to write down any non-zero digits that come after the 4. So 4.16 times 10 to the power of. Now, what we have to do is we have to count the number of digits after the first 4 here. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And so we're going to put in a power of 13. Now note, the power isn't the amount of zeros, it's the amount of digits after the first digit. Just make sure after that to write down kilometers because we are given the units in this question. So that's the distance from Alpha Centauri to our sun. Interestingly, Alpha Centauri is the nearest star to Earth, obviously with the exception of the sun. It takes 4 light years, roughly, for the light from Alpha Centauri to reach Earth. So when you look up the sky at night and you see the closest star to ours, which is Alpha Centauri, the light that you're looking at from that star has taken 4 years to travel across our galaxy and hit your eyes, let's say. And that massive distance has been given to us here in the question. But now we were able to write it in a much more manageable way, which is 4.16 times 10 to the power of 13. Okay, so moving on to the B part of the question, which is more specifically related to the rules of indices. So on the right hand side here, I have taken from the formula book the rules of indices. And so we'll have a look at which of these rules we need to apply for these questions on the left hand side. So the first question, so we're told to express 3 to the power of 10 times 3 to the power of 10 times 3 to the power of 10 in the form 3 to the power of n. So I'm just going to write it down: 3 to the power of 10 times 3 to the power of 10 times 3 to the power of 10. So in this example, we have 3, which is called the base number, and then 10 is called the exponent. So they're just the names of those parts of the power. So 3 to the power of 10 is 3 by 3 by 3 by 3, multiplying 3 by itself 10 times. And then obviously you're going to multiply that by another 3 to the power of 10 and another 3 to the power of 10. But we have a rule, the first rule here says that if you multiply numbers and they have the same base number, you can add the powers. So the rule here is if you have a to the power of p times a, the same base number, to the power of q, a different power, you can write it as the one base a, and then you can add the powers p plus q. So that's what we're going to do in the first one. We have the same base number with the 3 terms that are being multiplied: 3 to the power 10, 3 to the power 10, 3 to the power 10. So the base number is 3, and then we're going to add 10 plus 10 plus 10, and that gives us 3 to the power of 30. So if you multiply 3 to the power 10 by 3 to the power 10 by 3 to the power 10, we can use the first rule of indices up here in the top right to narrow that down, or to simplify that to 3 to the power of 30. Now the next one is a good bit more difficult. The next one says, well, what if we add 3 to the power of 10 plus 3 to the power of 10 plus 3 to the power of 10? Now there isn't a rule over here on the right side for adding the same base number. If we have the same base number and we go to add those, we haven't got a rule for those. So this is going to take a bit of cleverness for people to see that 3 to the power of 10 plus 3 to the power of 10 plus 3 to the power of 10 is 3 times 3 to the power of 10. And then people might see, well, if you have 3 to the power of 10 multiplied by 3, well, 3 at the front is the same as 3 to the power of 1 times 3 to the power of 10. And now we can apply this same rule number 1 up here, which says that if you have the same base number, you add the powers. So if we add 1 and 10, we get 3 to the power of 11. So ordinarily we would not be able to add base numbers with powers, but because the powers were the same in each of these terms, we were able, with a bit of cleverness, to say that this is 3 times 3 to the power of 10, change 3 to 3 to the power of 1, which it is, and then we could use this rule of indices where if the base number is the same, we can add the powers. Okay, the last question, we have 3 to the power of x equals 1. And the important thing with this question is to have a look at this rule here, rule number 4, which says that any number to the power of 0 is 1. So if I have 5 to the power of 0, that's 1. If I have 4 to the power of 0, that's 1. 7 to the power of 0 is 1. If I have a variable x to the power of 0, that's 1. Well, what would 3 to the power of 0 be? Well, 3 to the power of 0 would clearly also be 1. So if we come over here to the left-hand side, what does x have to be? Well, if we have 3 to the power of something and we get the number 1, that something, x, must be equal to 0. So that indices question is pretty tricky. The first part is reasonably straightforward because we just apply rule number 1. The second part is tricky because you have to spot that we can say that this is 3 times 3 to the power of 10. And then the last part just requires us to remember this rule here, that anything to the power of 0 is 1. And so if we have a number to the power of 0 and we get 1, well, that power must have been 0.